What's up, peoples? This video is to help you with the concept of buoyancy, which you can see as already written here, is the upward force of a fluid on an object. And by the way, a fluid could be a liquid or a gas. That's why some helium balloons float, because of the buoyant force of the air on that balloon. And the buoyant force is actually equal to the weight of the displaced fluid, as in literally mg. So let's derive an expression for this buoyant force. You already know that the deeper you go, the more pressure there is created by that fluid. So we have a cylinder in this fluid here, and it's feeling some pressure from above, like there is pressure of the fluid on the top portion and on the sides. As we go deeper, though, those forces of pressure become bigger as we go deeper and deeper and deeper. By the way, AP loves to give you free body diagrams of pressure vectors acting on an object. Make sure that as it goes deeper, you show the vectors getting bigger. And then on the bottom, it's the greatest down here. You can tell the bottom vectors are bigger than the top vectors there. So this is the pressure at the top, and this is the pressure at the bottom. And what we're going to do here is derive the expression for the buoyant force. Okay, here we go. Good times. The pressure difference creates a force difference. You can tell that there's more pressure pushing up. So that is going to be the result of the buoyant force. So F sub buoyant equals the force at the bottom minus the force at the top. And don't forget that pressure equals force over area. So force is just pressure times area. So the buoyant force is going to be equal to the the pressure at the bottom times the area at the bottom minus the pressure at the top times the area at the top. Now you may be asking, why are we not dealing with the sides? Hopefully you can tell that the vector to the right and the vector to the left, all these pressure vectors will actually add up to 0. They cancel each other out. Hello, we're going to scroll a lot apparently. All right, let's get to this. Let's keep deriving. Now, pressure is just rho GH. So we have F sub B is the density of the fluid. I would like to stress that. That is the fluid. G H at the bottom times the area minus rho of the fluid, the density of the fluid. G, the height or depth at the top, times the area. We can reduce this down a little bit more. We get the buoyant force is equal to, sorry, I wrote capital B. Sometimes I go back and forth. Oh well. Rho for the fluid, G area times the height or depth at the bottom minus the height at the top. Again, those are depths. And what we get here is, I don't know if you notice this, but area times height here, that is volume. So we end up with the buoyant force is equal to rho times the volume times G. This is our buoyant force. And that is the density of the fluid. I just want to remind you that this is rho for the fluid that the object is in. I don't know why my pen is not acting well here. I would also like to add that I think you know, that density equals mass over volume. So if I sub that in here, I get mass over volume times G, and you know what that becomes? That becomes mg. But remember, this is the volume of fluid displaced. This is the mass of the fluid. So this actually becomes the weight of the fluid. So the buoyant force is equal to the weight of the fluid that you displace. That was another definition. All right, let's put this to use. Basically, the buoyant force is a force. Forces go in free body diagrams. That's pretty straightforward. And a lot of the things we do when it comes to buoyancy are static, meaning not moving. So the sum of the forces is going to be 0. We've got acting on this ping pong ball, which is submerged in water and tied to a string. You've got the buoyant force, you've got the force of tension, and you've got the force of gravity acting on that ping pong ball. Let's get to it. We haven't used purple in a while. Why don't we do a little purple? I don't know if you can hear that beeping in the background. That is the sound of bacon cooking in the oven. All right. Sum the forces that equal 0. They're going to add up to 0. So you have the buoyant force minus the tension minus the gravitational force. I'm taking my time with this, writing it out slowly. You may not need to do this, but the buoyant force is equal to the density of the fluid. Don't forget it's the fluid. Volume times G minus the mass of the ping pong ball, because it's the ping pong ball, times G equals Ft. Density for this fluid, we're going with water, so it's going to be 1,000 kilogram per meter cubed. The volume is the volume of the displaced fluid, and this is a spherical ball, so that's going to be 4/3 pi times the radius, which I happen to look up. These are correct for a ping pong ball. 0.02 meters cubed times 9.8 meters per second squared minus the mass of the ball, which is 0.0027 kilograms times 9.8. Sorry if this is boring you, equals Ft, and we end up that the tension force is equal to roughly 0.302 newtons. Not a bad problem. Seriously, we drew an FBD. One of the new forces is the buoyant force. We've done these things before. We get friction, we do MUFN. We get a spring force, we do KX. Now we got a buoyant force. We do rho volume G. Done. Let's move on. What if we replaced this ping pong ball with a ping pong ball filled with some kind of concrete or something? All right, let's do another quick example here. FBD, so this thing would sink if it wasn't for this string. So we've got tension acting up, the buoyant force acting up, and we've got gravity acting down. Sorry, I tried to draw those to scale so they add up to 0. And then we do our sum of the forces as per usual. That's an ugly looking color. Let's go with it. We do the sum of the forces is going to be 0 newtons. You've got tension up plus the buoyant force up minus gravity acting on this ball down equals 0 newtons. So we get tension is going to be equal to the buoyant force, which is density of the fluid, volume times G, minus mass of the ball times G. So tension is going to be equal to 9.8 meters per second squared. I just factored that out. Density of the fluid, which is 1,000 kilogram per meter cubed. Volume is going to be 4/3 pi r cubed. Oops, sorry, one too many zeros. 0.02 meters cubed minus 0.07 kilograms. And when you do this, you get a tension force of 0.652 newtons. Not a big deal. Again, what did we do? We drew a free body diagram where one of the forces was the buoyant force. All right, last one. Oh, not last one. I lied. Let's do this one. First, we're going to start with a free body diagram. This is some kind of cube floating in a liquid. I'm going to just draw a free body diagram. So we have F buoyant has to equal the force of gravity because it's just chilling on this thing. Your next step, of course, is to start with the sum of the forces is going to be 0 newtons. Sorry to jump to this so quickly. I just felt like you might be getting bored listening to me do math. So here's the deal. We started with the sum of the forces was 0. And that means the buoyant force has to be equal to the force of gravity. Okay, now the buoyant force is the density of the fluid times the volume times G, and the force of gravity is the mass of the cube times G. So we're here right now. That, obviously, the G will divide out. Now, the volume of displaced fluid, since it's a cube, there, sides of length L, we'll say. Well, the volume that's displaced is the area, L times the depth, which is the height. So that's where the L times H comes from. And you can see that in this diagram here, that the length of the sides are L, but the volume that is submerged is the area, cross-sectional area, times the height. As for the mass, don't forget that mass is density times volume. Okay, so I subbed that in, but this is the volume of the cube, the actual volume of the cube. We need that to get its mass. So that's the density of the cube times the volume, which is L times L times L. And so two of these L's are going to divide out, and I've rearranged things here. And this is an expression that you're expected to know for AP. If I take the density of the cube and divide it by the density of the fluid, that gives me H over L, or literally the amount of the object that will be submerged. Okay, let's move on to our last scenario here, okay? Here is a polar bear standing on a cylindrical piece of ice, and we want to know the mass of this bear that can stand on this thing before it starts to sink. Guess what we're going to do first? Take a wild guess. I'm going to go with a free body diagram. So this is about the ice. Okay, we've got the force of gravity acting on the ice. That's force of gravity on ice. We've also got the force of gravity caused by the bear. But then we've got the buoyant force holding it up. So let's do this. As we've done with all these problems, the sum of the force is going to be 0 for a while. Maybe we'll change that. You've got the buoyant force minus the force of gravity on the ice minus the force of gravity on the bear. They're all going to add up to 0. And then the buoyant force, this is going to be the density of the fluid, which is going to be seawater in this case, the volume of fluid displaced times G, minus the mass of the ice times G, minus the mass of the bear times G equals 0. And conveniently, G will go bye-bye. Then we've got, don't forget, as per usual, mass equals density times volume. So we're going to be subbing that in there. And we've got the density of the fluid. That's going to be the seawater. Volume that is displaced. We're assuming that this guy is just about to sink, or girl, either way. And so the ice is completely submerged and just under the surface. So this is going to be the volume of a cylinder. So it's going to be pi r squared times the height minus the mass of the ice, which is density of ice, and the volume of that thing. Why am I writing an M? Anybody know? I don't know. Pi r squared h equals mass of the bear. So let's do this. The mass of the bear ends up being pi 2.5 meters squared. The height of this cylinder is 0.5 meters. And then it's the difference in density. So the fluid is 1020, 1030. I think it's 1030, right? I don't remember. I don't want to scroll up. I'm too lazy. 1,030 kilograms per meter cubed minus the density of the ice, which is 920 kilograms per meter cubed. And we end up with the mass of a bear. That's actually a little too large for this problem, but okay. Turns out most polar bears are around 1,000 pounds. This one's around 2,200. So I may have messed something up. But also, let's go back to that thing about ratios of densities. It tells you how much that was submerged, right? We did that on the previous screen where we had the density of the object. So in this case, the density of the ice over the density of the fluid. will tell you how much of that ice is submerged. Well, that's 920 kilogram per meter cubed, and this is 1030 kilogram per meter cubed, and that gives us a pretty big number. I don't remember what it is, so I'm going to do it in the calculator really quick while I talk, and we'll come up with 89.3%. So when you see the tip of that iceberg, what it's telling you is that almost 90% of that iceberg is underwater. I don't know, my thing is acting up. That's pretty fascinating. You're just seeing a little bit while the majority of it is underwater. That's fascinating. I wonder if the Titanic knew that. Oh well. Poor Jack. Anyway, let's wrap this amazing video up. First of all, buoyant force is an upward force of a fluid on an object, and it's equal to the it's equal to the weight of the displaced fluid. Our equation is rho vg, where rho, or the density, is the density of the fluid, and v is the volume of fluid displaced. Other than that, there's really not much to it. We've summed that up here with the buoyant force being equal to the force of the weight. As always, it's a force. Draw an FBD, do the sum of the forces. And also this little known thing is that the ratio of densities tells you how much is submerged, what percentage. If you know the percentage, you might be able to figure out the depth. And I'm only bringing that up because it shows up in AP multiple choice on a regular basis. So that's it. That's buoyancy. It's a force. Let's add it to our repertoire of forces. Repertoire? Or should it be like armory? I don't know. We have a lot of them. Anyway, I'm rambling. This was not one of my best videos. There were a few distractions during this video that caused it to be less than okay. But you know what? I'm still amazing. So I'm going to give it 3 out of 5 stars. Hope it's been helpful.